So centripetal motion gets a little more in depth with the topics you can see here on the screen. Level curves, bank curves, horizontal circles, and vertical circles add some complexity and application to what we've already talked about with centripetal force. Normally, we would study these more in depth than we are going to this year, but they we are still going to have the opportunity to learn a little bit about their application here and through some WebAssign problems. Note that College Board most likely will not ask questions directly related to these on the AP exam this year with the format that it's in, although they may ask about some theory related to these, but not necessarily problems. As you're going to see, the equations that we're going to derive here are not on your AP equation sheet. And with the time allotted for this year's test, I don't imagine they will have you go through these types of derivations. We will study these more. For those of you that are coming back for AP2, we'll study these more. We go to the amusement park during the fall. Hopefully, we'll be able to do that, and we won't be still socially distancing. But when we do have an opportunity to get to the amusement park, we will study these in depth, taking measurements and validating some of the equations we're going to be seeing here. To start off, we're going to do a basic concept of a level curve. We already did a little bit of that, but I'm going to give an example here. So imagine you have a car, and that car is driving down the road. And as it's driving down the road, it is going around a corner. When that car goes down the road and around the corner, there has to be a force that causes it to bank around that corner. If there wasn't, the car would continue in a straight line. If you ever had the unfortunate experience of driving down the road on an icy day and turning your wheel and having your car continue off in a straight direction, which does happen, it's the inertia of the car, you would know immediately that there is no centripetal force. And you might already be guessing what causes that centripetal force, and that is friction. And as I said to you in the last video, there's always something that is causing a centripetal force to exist. Centripetal force isn't something that comes by itself. So when we take a look at this problem, what we find is that as the car is going around the corner, there is a force inward of friction. And that you may not exactly see here in this straight point, but as it's coming around this corner, the wheels of the car are trying to slide outward, and it is friction that keeps pulling it towards the center of the circle. And so the friction is acting as the centripetal force. And so mg mu cosine theta is equal to mv squared over r. Remember that this was for a flat curve. And so for a flat curve, theta would be equal to 0, so the cosine of 0 is 1. So we end up with a simplified equation of mg mu is equal to mv squared over r. The m's cancel out, and we get a very simple g mu r is equal to v squared, or v is equal to the square root of g mu r. And if you ever had that experience of going around a corner and not having your car continue around that corner because of a lack of friction, you would say grr. And notice that's what we have here, grr. That equation says to us that as the coefficient of friction goes down, the radius has to go up to keep the velocity the same. So we can't change gravity. So as velocity goes down, we are able to have a lower coefficient of friction. But if we want to keep our velocity the same going around the corner, then the radius has to go up. And so instead of that means that when the friction goes down. So if friction goes down, instead of following this general curve, now we're following something more like this. So that is the equation for a flat curve. And you could see that right here.